Uh, right, let's start. Today, we'll kind of wrap up the statistics portion of this course, roughly the part 2 of this course, uh, and then start discussing about coding theory, or in particular about error correcting codes. Um, and also homework 3 will be out by tonight and should be due next week by Friday. I'll post an announcement on Canvas soon. Okay. Just a reminder on what we discussed last time. We sort of talked about this operation of finding the minimizer of the KL divergence between P and Q when P varies over a set, in particular a closed convex set. And this is the quantity which sort of showed up in a lot of bounds when we were doing hypothesis testing or concentration bounds, etc. So we talked a little bit about what are the properties of this quantity, or what are the properties of this minimizer in particular. And an important case which we discussed was when the set of distributions is kind of defined by expectations of a list of functions, f1 to fk, and these are called linear families. And we sort of, I guess, proved this by example, considering the case of one function, but the proof generalizes that when you have a linear family, then the minimizer, or this function p star, has a nice form. In particular, it belongs to an exponential family, or rather, the probabilities are basically just scalings of the probabilities of Q, and the scaling only depends on each of these functions whose expectations you care about. Okay. Any questions about this before we proceed? Okay. So one nice application of this, which I wanted to show before we kind of proceed to coding theory, is to a problem called matrix scaling or synchron scaling. And this problem itself comes up in finding deterministic approximations of matrix permanent, sort of gives maybe a somewhat weird algorithm for bipartite matching, but then it's useful in some settings. And also it has some nice generalizations to what are called operator scaling questions, which have been kind of a fairly active area of research recently. So I wanted to just talk about what's called Synchron's matrix scaling theorem, which just is an equivalent way of stating it, is that if you have a matrix with non-negative entries, so let's say all entries ij are greater than 0, positive entries, not just non-negative, then we can kind of scale the rows and columns so that sort of every row sum and every column sum becomes 1. Okay. There are more general versions where you have some sort of target matrix and you want to change the row and column sums of your starting matrix to be the same as the target matrix. But this case is kind of the one that is used most often, and the proof will give you the general case also, but it's easier to state here. These kind of matrices are called doubly stochastic, where the sort of rows and columns all add up to 1. And the interesting thing is you want to kind of multiply each row by a number and each column by a number. So in particular, we will have ijth entry to be the ith diagonal entry of the first matrix times the original entry of the matrix times the jth diagonal entry of the second matrix. And so you sort of choose a fixed number depending on each row and fixed number depending on each column and multiply entries that way. And the nice thing is we can claim that the matrix sort of becomes doubly stochastic. And Synchron's proof of this is kind of an example of what is called alternate minimization in some way. So if you just had to change all the row sums to 1, then you just kind of multiply each row by a constant, which is kind of 1, the reciprocal of the current row sum, and then the row sums will become 1. If you just wanted the column sums to be 1, you just kind of multiply every column. And Synchron's algorithm is that if you kind of keep iteratively doing this, you actually get a matrix where both row and column sums become 1. We'll give a different proof of this using showing the existence using what we know about kind of KL divergence or minimization of sort of KL divergence over a convex set and so on. But it's a cute proof, and in particular, it illustrates what I was saying last time, that sort of in a lot of cases, it's not the minimizer itself which we care so much about, but the specific mathematical form of the minimizer in particular. For example, that linear families, it looks like something coming from an exponential family. And this is an illustration where the form is really important, and that's what actually gives us the theorem. Okay. Before we start, let me just change the problem a little bit. So instead of asking the row and columns to sum to 1, I'll just sort of change it a little bit, and I'll ask it to sum to 1 over n. We can kind of, again, multiply rows and columns by an additional root n, and then things will become 1. So that's not a big deal. But let's just, because with this condition, the entries of the matrix, because there are n columns, each column sums to 1 over n. So the sum of all the entries is 1, and we can think of the entries of a matrix as a distribution. They are kind of positive numbers which sum up to 1. And so then we will kind of apply all the machinery we know about distributions and divergences. So let's start. Let's say we take our original matrix and convert it into a distribution. So basically we take capital B to be the sum of all the entries in our starting matrix, divide all the entries by capital B. So now all the entries add up to 1. And so we get a distribution. So another way of saying is that we have a distribution now, which is this matrix, and the distribution can be thought of as on I comma j pairs. For every I comma j, we have a sort of probability written in that box of the scaled matrix. And what we would like is to modify it to a different distribution, which is kind of given by this m prime, such that every row in this new distribution adds up to 1 over n, and every column in this new distribution adds up to 1 over n. And that looks a little bit like linear conditions, and in fact, we will kind of phrase it that way. So let's think of writing down the conditions we want on our target distribution P, which is that P is a distribution such that every row, or it's a distribution with probabilities written in the entry of a matrix such that every row adds up to 1 over n, every column adds up to 1 over n. And I claim that we can write it as a linear family in the form that we have looked at before. But yeah, I'll maybe ask you to tell me what are the functions that we should be talking about. So can we write the first condition in the form written in the second line for some specific choice of functions f sub l? So see, this function is kind of summing up all probabilities weighted by the value of the function. And we want each function to only sum up the probabilities in a single row or only sum up the probabilities in a single column. So let's define indicator functions. So let's define functions where fi0, which takes ij and is 1 if we are talking about some entry in the I0 row and is 0 otherwise. Similarly, let's define a function g sub j0, which takes an entry ij and kind of only activates if we are talking about the j0 column. And now we can rewrite what we have as saying for each of these functions, So in total, we have a collection of 2n functions. And we can write all the conditions we want as sort of moment conditions on these 2n functions. Sorry, just a second. Okay. So we have these kind of indicator functions for rows and columns. And in the spirit of sort of what we were discussing before, that if you want to search for an object, we have certain conditions on that object, then a kind of generic idea is to search for the maximum entropy object, or maybe the closest object satisfying these conditions. So we will sort of do something similar, that we will search for we want these properties, and we are starting from a distribution Q. So we will kind of try to look for an object satisfying these properties, which is maybe as close to Q as possible. And this is also called the projection of Q to this linear family. We already know that this projection looks like it has a nice form. In particular, it belongs to an exponential family with this sort of, now with some multipliers, lambdas and mu's. I just want to distinguish the row functions and column functions. And now let's recall what these functions are, right? So this function is 1 if I is equal to I0, and this function is 1 if j is equal to j0. So in particular, when we are summing over of all these terms, if we are calculating for a fixed ij, only one of these will be non-zero, in particular corresponding to the first coordinate of that tuple ij. Similarly, here only one term will be non-zero, and so we'll just get e to the lambda I and e to the mu j. And now this sort of looks exactly like the form that we wanted, that you're taking some entry of mij, multiplying it by some number which depends only on the row index, some number which depends only on the column index. So in particular, we can take the ith entry of the first diagonal matrix to be, let's say, square root C0 over B. Times e to the lambda I, and this to be square root C0 over B, e to the mu j. And then we get the property that we want, that because we have that P star ij is in our linear family. So in particular, it has the property that probabilities in each row and each column add up to 1 over n. We have this property that if we look at maybe root n times d11 times m times root n times d, d1 times d2, this is doubly stochastic. So it's just a simple example where it's more important what the form of the minimizer looks like, in particular that it has an exponential family. This is an alternate proof of Synchron's theorem, just using the properties of kind of maximum entropy distributions, or this kind of I projections in this case. It also, because we kind of found this scaling as a minimizer of KL divergence or minimizer of a convex function over a convex set, you can also use this to develop algorithms, and in fact, really fast algorithms for computing these kind of diagonal matrices. Yeah, so it's not only gives the proof, it actually gives the fast algorithm. And also, it kind of has generalizations to other settings, such as operator scaling, etc. I'll leave as an exercise the question of where did we use that all entries are non-negative or are positive, really. Non-negative we used because we thought of things as a distribution, but where did we use that they were all positive? Okay, any questions before we proceed? Okay, so that was a sort of application of what we discussed last time, and that roughly wraps up a discussion of information theory to statistics. And in particular, we talked about kind of statistical problems with n independent samples. So from some possibly unknown distribution, from one distribution in a family and so on. And we talked of Sanoff's theorem, which tells us roughly what is the probability that n samples from a distribution Q look like they're coming from some other distribution P, maybe sort of for one P in some large family pi. Hypothesis testing is again a sort of question of this form, that we want to distinguish a bunch of distributions from each other. So we want to kind of figure out what is the probability that the samples, when they're coming from one distribution, they look like they're coming from the other one or something close to the other one, or one of the others if there are many of them. Minimax rates was about kind of finding properties of distributions, but then we also sort of related it to hypothesis testing, saying that if we can estimate these properties well, then at least for a bunch of separate, sort of well-separated distributions, we can think of it as identifying the distribution. And then the quantity that showed up in all of these calculations was some sort of minimizer of KL divergence in a set pi, which we saw, which we call the I projection, at least when pi is a closed convex set. It also captures the nature of maximum entropy distributions, and we can study the form of it for some special sets pi. So a lot of it is about, yeah, in some sense, just this idea of what is the, how to understand that samples from one distribution look like they're coming from some other distribution, and then there are applications of sort of quantitative forms of this statement. Any questions about the statistics portion, about one of these, about the connection between them or anything before we proceed? Okay. The next topic, which we'll talk about for this week and the next one is, maybe later if needed, is kind of channel coding or error correcting codes and so on. It's a so the setup is roughly the following, that we want to send a message, and let's think of this message as, so I should say that there's so-called kind of Shannon model and Hamming model, and I'm going to describe the Shannon model first, and let me come to the Hamming model later. So Shannon model is sort of related to the information theoretic things that we have looked at, where you want to send a message, let's say uniformly chosen in some space 1 to m. And the way we send it is we get to kind of fiddle with this message. We want to kind of rewrite it in whatever way we want. So we have some sort of an encoder which maps this message to strings of length n in some finite universe script X, as always. And then we send this kind of encoded message, or this string of length n, through some what is called a channel, where and we're kind of studying a special kind of channel here, which is called a discrete memoryless channel. So discrete because the universe over which the messages are kind of, or this area script X is finite. So we're going to say script X is finite. Okay. And memoryless is that each xi is treated independently. independent of history. So what does this mean? So I'm sending sort of a string of length n. This channel is some sort of abstraction of what kind of noise can occur when we are trying to communicate. So what this means is that, but the memoryless property means that when I send the first position element of my string, the channel will possibly introduce some noise, which is captured by this kind of a distribution, p, y given x. So it takes x as an input, it has some distribution over what the outputs can be, and it sends out the output accordingly. And then I send the second element of my string, and the same thing happens to the second element, independent of what happened to the first element, and so on. So it doesn't really depend on the history. Okay. Okay. Before, there are a few assumptions, all of which we can question, starting from the fact that we are sending a message which is uniform. Earlier, we kind of tried to send a message where there was some sort of distribution over the messages, and we tried to capture this by the entropy of the set of messages, etc., or the distribution. But the way we kind of consider this is we kind of decouple two parts. So you do what we discussed in the first or second lectures, that you sort of try to send a message as based on what is the distribution you have on messages. Once you kind of send a long enough sequence, we saw that you can sort of compress things well, but using something more, which is called an asymptotic equipartition property. But I mean, roughly that if you try to send using this sort of compression scheme, that at least if you look at long sequences of messages, they all look roughly uniformly distributed over some space. So it kind of decouples these two things. The compression part is first, then once you're done with compression, then the issue of kind of communicating reliably or trying to send something where there is no errors. And here we can kind of assume that things are uniform after the compression step. But these two parts can be studied independently, and a lot of the interesting ideas will just be about this part of the communication. The next part, the encoder, yeah, I mean, right now we are just allowing it to be whatever we want. The channel, again, doesn't necessarily have to be discrete, doesn't necessarily have to be memoryless. There are many other kind of possibilities, but given that this is kind of the most representative case for the channel model, and given that we'll sort of spend few lectures, this might be the case where we'll sort of try to prove things formally. And there is sort of the other extreme of it, which is something we will also talk about because it's kind of fairly useful in computer science applications, where we have a message which is chosen arbitrarily. So there is no distribution. There is no probability. Sort of, we just want to pick a message and send it reliably. Okay. The encoder is again kind of arbitrary. And the channel can do sort of adversarial errors. So there is no memoryless property, nothing. It just sort of takes a look at the entire string I'm trying to send and can do whatever it wants to the string. As stated, the problem is completely hopeless because the channel can always send 0. Right? I mean, no matter what I try to send, the channel will say 0. So, I mean, obviously, I can't hope to communicate anything. So, so the way we kind of formalize this problem is that we bound the number of errors. So out of n positions, it can corrupt up to t positions, let's say, and t will be a parameter. But beyond that, things are sort of arbitrary, and the goal is to try to send any message that I want reliably as long as there are no more than t errors, adversarial. This is a bit more useful in, so this is not kind of a probabilistic model, but it's fairly useful in applications in computer science. So this is the sort of other extreme that we will look at. And in between, there are many options. What if sort of there is some weak dependence on the history? What if the adversary is not completely kind of adversarial or arbitrary, but it can only do some limited amount of computation? What if it can only store a little bit of information about the sort of encoded string and so on? So, but hopefully covering these two extremes will give some flavor of the literature on error correcting codes. The questions we'll be kind of interested in are, first of all, so what can be done? So in some ways, can we measure how much information can we communicate? What is the probability with which we'll be correct? And so on. How much can we find these kind of codes? What do these kind of encoding schemes look like, possibly depending on the property of the channel? Because the kind of computer science people, can there be sort of, usually encoding is easy, but what are the algorithms for kind of encoding, decoding? How do we kind of correct noise? How fast can we do this? And one thing which we will not discuss too much is applications of coding to other areas. So, I mean, the way we kind of phrased it, we're just sort of phrasing the problem of coding itself as a mathematical problem. But like anything else, a code is a mathematical object which we can apply in other settings. So we can think of, I mean, an algorithm as kind of basically solving a decoding problem while the algorithm is for some completely different question. Or we can sort of try to construct an object, and maybe we saw that, we claimed that this kind of separated vectors in the mean estimation problem that we constructed basically formed a code. So there are sort of applications of codes as mathematical objects to a variety of other areas, not necessarily related to the question of communication. We will not discuss a lot about this, but a lot of properties of the codes, or some sort of structural properties of codes, are often useful in different applications. For example, there is the famous PCP theorem, or theorem of probabilistically checkable proofs in complexity theory, which is essentially a theorem about existing of some very good encoding schemes. And so, I mean, yeah, there's a lot of applications to this kind of this abstract framework of encoding, much beyond this sort of problem of communication, but we will not be able to discuss all of that. And just while we are talking of connections, I mean, in some sense, the question we have been discussing about statistics is also related to at least some kind of a decoding problem. So the universe wants to send us a message. What is that message? It's a distribution. It's a property of a distribution. It's some parameter maybe we want to understand, whatever. There is some channel which basically sends us n independent samples from this distribution. Okay, so this is some kind of noisy version of the message the universe wanted to send us. We just get n samples. And what we were doing was decoding. So we were trying to kind of estimate a property or identify the true distribution or whatever by looking at these samples, which are possibly noisy form of communication, and then we want to do the best we can. The crucial difference here is that we have an encoder. So we don't have to send the message, or like in there, we didn't have a choice of saying that, okay, I know you would really like me to kind of look at a distribution with mean mu, but would you mind sending me samples from a distribution with mean kind of mu square plus 3 mu instead? I think I can do much better with that. We didn't quite have this luxury in the sort of statistics setting. But here we get to sort of pick an encoder-decoder pair, and a lot of the kind of questions about error correcting codes are kind of picking a good encoder-decoder pair, whether the good means algorithmically, explicit, some other properties, whatever. Okay. So in some sense, it's an extension of the ideas, with the crucial difference that we now get to pick an encoding. Any questions before we proceed? Okay, So this is just a reminder of the objects that we were looking at. We have some distribution or uniform distribution, a set of messages, some encoder, some decoder. For now, we are just going to think of them as functions, the encoder and decoder both, let's say deterministic functions. And same here. We'll come later to these issues of algorithms for finding these functions or actually computing this. A couple of important quantities that will sort of play a role in the initial discussion today is what is called the rate of communication, which is kind of per channel use or sort of per symbol that I transmitted, how many bits of information did I actually send you? So if I can reliably communicate, and we'll get to that in a minute, what it means to communicate reliably, then I'm sort of overall sort of sending you one of m possible messages, and I'm thinking of the uniform distribution, so the entropy of the set of my messages is log m. And I'm using the channel n times to send it to you. So per transmission, I'm sending you log m over n bits of information. So that's roughly how we think of as this number defining the rate. And the capacity of the channel, this is a quantity we kind of talked about earlier as an example of computing mutual information. We'll sort of see much more about it. It's a so remember, the channel itself is specified by some distribution which is conditional. So if I send a symbol x, what does the outcome y look like? Right? The joint distribution is not yet defined because we haven't sort of decided what the distribution of x is. Okay. So the capacity of the channel is said to be the maximum mutual information we can have between the input and the output if we are free to choose the distribution of the input. So is the definition okay? So once we kind of fix the distribution of the input, the conditional distribution is fixed by the channel. And so the capacity, which is now a function of the joint distribution, is a quantity we can compute. And we'll see a relationship between rate and capacity in a bit. But for now, I just wanted to make sure the definitions are okay. Okay, so let's look at some examples of channels. So let's say the channel is kind of perfect. There is no noise. You sort of try to send a 0. So in all of these examples, what we are trying to send is a sequence of bits. So each channel use will try to send either a 0 or 1. And if we try to send a 0 or 1, these kind of diagrams, or these are transition probabilities, will capture what comes out at the other end, or what is the distribution of the outcome at the other end. Okay, so let's do a few computations. The first case, the channel is perfect. You send a 0, you get a 0, you send a 1, get a 1. What's the mutual information of x and y? So you can write, in each of these cases, you can write the mutual information in terms of the distribution p of x, and then we will try to optimize over p of x. So you can write in terms of the distribution. Any guesses what happens in the first case?
It should be n, right?
Okay, so the mutual information, actually, we are defining it for a single channel use. So just a single symbol x and a single output y. We are not worrying about, because the channel kind
Oh,
of
okay.
dependently on every symbol. So we are only talking about one symbol at a time. Okay. So all these diagrams and everything are for single channel use. So we're just sending either a single 0 or a single 1. So how much should it be?
I would say 1.
1. Why is that?
Well, hx conditioned on y is 0 because it's fixed. So that goes to 0, then h of x, and we're uniform.
Right. So it's h of x, and then if we are trying to look at x is 0, 1, and then we are trying to maximize over the, so this is the mutual information, and then we are trying to look at the capacity, which is the maximum of the mutual information over the distribution of x, right? So, and so we are basically maximizing the entropy of x, which is distributed over the universe 0, 1, over all distributions, and we know that the maximum entropy it can have, and it's achievable, is 1. So the capacity of this channel is 1. And I mean, in some sense, like at least if m is a power of 2, it's easy to see that you can actually have that also as a rate. If m is a power of 2, let's say 2 to the 3, so you have 8 possible messages. You kind of write them as numbers between 0 and 7, which are 3-bit strings, and then you send each string bit by bit. And because the transmission is perfect, send a 0, get a 0. So whatever you send is received at the other end, and you communicate your message perfectly. So here, it's kind of easy to see that the channel capacity is 1. Also, we can have transmission with rate 1, at least when the set of messages is a power of 2. And we'll see kind of a little more about the rate, which will kind of get rid of this issue. Right. The next example is a bit more interesting. So now the output is not 0, 1. It's some other letters, let's say A, B, C, D. And they're kind of randomly distributed based on what your input was. So you either get randomly A or B or get C or D, depending on whether you sent 0 or 1. Any guesses now about what happens? Or not guesses, but computations.
Madhur, a question.
Yes.
So here, so this probability P distribution is being decided by the encoder, right? We're assuming that the messages are uniform. And then once I fix my encoder, this P of X is fixed.
Yes. So yeah. So right now I'm not relating it to the encoder. I'm just asking a question of computing the capacity of the channel where we are allowed to pick the distribution P for free. But you're right that it will come from the encoder. So basically, we will design or we will try to come up with codes which, when we say we can achieve capacity, we will try to have an encoding scheme such that the distribution of the input looks like this P.
Okay. Thanks.
Yeah, but for now, like forget about the encoding question. This is just a question about mutual information. And of course, you're allowed to choose P for free right now. We will see how this relates to the encoder in a bit. Okay, I get a vote for 1. It's the same proof. So y is random, but if you are given the value of y, you know x. Y could, like if y is either A or B, you know x was 0. If it was either C or D, you know x is 1. You don't really need to know sort of like, even though y has some entropy, x given y has no entropy. So the capacity of this channel, although it has some randomness in the output, the capacity is still 1. Which, by the way, is the maximum we can hope for because the mutual information is always upper bounded by the entropy of x. And the entropy of x can be at most 1 in this case. Okay, now let's look at what is called the binary symmetric channels. So the communication is noiseless with probability 1 minus p, and with probability p, you kind of flip what you were trying to send. So 0 becomes a 1 or 1 becomes a 0. So it's symmetric in terms of what happens to 0 or 1, but there is some amount of noise. And this was kind of one of the exercises way back when we talked about mutual information, to sort of compute the mutual information and also maximize it. Any guesses, computations? Something you recall from earlier computation?
I think this one is easier to compute with the h of y minus h of y given x expression.
Yeah, that sounds right. Okay, let's do that.
So because it's symmetric, this h of y term is, or yeah, maybe I should leave that off. The h of y even x is the interesting one.
Right, let's do that. Okay. Can you say what either of these terms looks like? Max?
I mean, I suppose the difference here to the exercises, we were given a distribution for x, and without.
Yeah, so I mean,
that's the maximum entropy distribution, or the maximum information distribution. So I don't want to.
That's fair. So you can assume a distribution for x if you like. Let's say x is equal to 1 with probability q, 0 with probability 1 minus q, if that helps. So I claim that h of y given x you can compute even without knowing the distribution of x.
That term should just be binary entropy function evaluated at p.
Right. So this term, because I mean, yeah, you can write it in terms of the two values for x if you like. So you can say q times the entropy of y given x equals 1 plus 1 minus q times the entropy of y given x equals 0. But I mean, both of these are the same. You sort of, it's just kind of their flipped distribution. So if x is equal to 1, you have a distribution which is now 1 with probability 1 minus p, 0 with probability p. In the other case, you have a distribution which is 0 with probability 1 minus p, 1 with probability p. In both cases, the entropy is the same. It's the distribution which is kind of the biased coin, which comes up heads with probability p, let's say. So the entropy of it is equal to the binary entropy function evaluated at p. Okay, now let's go to the other term. What about h of y? So we can do this explicitly in the sense that what is the probability that y is equal to 1? It's that you started with a 1, which happens with probability q, and you kept it. or you started with a 0 and you flipped it. Those are the two ways in which you can end up with y equals 1. And I mean, yeah, we don't necessarily care, like, so it will be some number, let's say between 0 and 1. And kind of you and I, between us, we know that this will be maximized if this probability was actually equal to half. Right? Because we know that y is also a 0-1 variable, and the best entropy we can hope for is when it's uniformly distributed over 0 and 1. And we know that this is equal to half for p equals half. Oh, sorry, for q equals half. So P is kind of dependent on the channel. Q is what we are choosing, and we are free to choose. And here we know that we can kind of choose Q in a way that y becomes 1 or 0 with probability half each, in which case the entropy of y will be 1. And the second term doesn't depend on Q, so it will be still H2 of P. So the maximum we can hope for is, or which we can actually achieve, is 1 minus the binary entropy of P. And that's the capacity of this channel. Any questions about this? Kevin is asking Q equals 1 over 1 minus P. That's a number bigger than 1. That's not allowed. Q has to be between 0 and 1. Okay. All right. So here, the mutual information we can write down in this way, and we know that the maximum value which we can achieve is 1 minus the binary entropy of P. And I'll leave you to check that the capacity is equal to 1 minus P in the case of the so-called binary erasure channel. Okay. Where now it's kind of 0 and 1 are not kind of confused with each other, but they're just maybe deleted, and you get this symbol bottom, which is just kind of formal way of saying oops. It's the symbol got deleted, and we don't quite know which one it was. Okay. And a nice theorem which sort of relates these notions is what's called the channel coding theorem, which says that the maximum rate which we can hope for is the channel capacity that we wrote down. And not just something we can hope for, it can actually be achieved. But to define achievable, let's say a little more carefully. So first of all, we say a rate R is achievable if we have kind of a sequence of codes, maybe with n increasing, whose rate is at least R. And the probability of error goes to 0. So the encoding, decoding, after all of that, we still have some probability left, because the encoding and decoding are probabilistic functions, and it's possible that even though the channel has sort of maybe on average introduces only a small amount of an error, maybe with some kind of fluke, there was so much error that all our algorithms just went haywire. So there is, of course, a small probability, but as long as it goes to 0, we will say that we are kind of achieving this rate. Okay. And for a rate, we will say that we will achieve the channel capacity in the sense that sort of the supremum of all the achievable rates is equal to the channel capacity. So there is a sequence of achievable rates which converges to the channel capacity. That's not to say that we will have a code with rate exactly C, but we can get arbitrarily close to C. Okay. So for a rate which is C minus epsilon, we can have a sequence of codes with rate at least C minus epsilon and the error probability going to 0. Okay. That's the notion of what it means to kind of achieve a rate, or the fact that the channel capacity is achievable. And this is just kind of recap what we are doing in some sense. You can, yeah, it is a Markov chain. So you can think of this sort of the encoding. I mean, once you fix your encoding scheme, or once you fix your deterministic function which will do the encoding, the first part is really the same blob. Like W and X bar are the same thing. They are not. There is no kind of randomness in X bar given W. X bar, again, I'm going to think of it as a string in script X to the n. As is before, we were kind of thinking of these as X1 to Xn as X bar, and similarly for Y. Here, you kind of have this channel which sort of maybe perturbs every transmission independently in a kind of memoryless way. And then you kind of have, as before, some sort of estimator, something which tries to predict what the true message was. And we are, as usual, measuring the error probability of this estimator. Okay. The error probability is over the transmission in the channel. Everything else we are taking to be deterministic. Okay. I mean, the error probability, sorry, is over the transmission of the channel and over the choice of W. So the channel will do some error, will introduce some errors, and the initial W was also chosen uniformly randomly. That was our assumption from between this set of messages M. And we're kind of looking at the probability of error. Any questions about, I mean, we haven't proved this theorem at all. We'll talk more about it, but any questions about the statement, about the model? Okay. So, I mean.
Sorry, I guess I have
please.
Confusion. Why is the sequence upper bounding the rate?
Why is, you mean why are we looking at the supremum of the achievable rates?
No, that makes sense. But why that it's achievable, would there be a sequence of codes with
rate at least R?
Oh no, I think I understand now. Okay. Yes.
Yeah, it's just sort of, we write it this way to kind of get around these issues that maybe for some values of n or some number of messages, it might not be a power of 2 and so on, and all those will go away once you sort of define it this way. Okay. So, I mean, define it in terms of sequences, and then the inequalities on the sequences, I think, are natural, but if not, I'm happy to answer. Okay. So, we first want to prove an upper bound, which is that the supremum of the sequence of achievable rates is at most the capacity of the channel for any kind of discrete memoryless channel that we talked about. By the way I wrote things, you might have already kind of assumed that I'm going to use Fano's inequality. And as I said before, it's basically 3 variables. The first blob is the same thing. Sort of X bar is a deterministic function, and there is a bijection between W and X bar in the encoder. So that part we are not going to worry about. The next part is what we are going to think of as a Markov chain, and we know from Fanon's inequality that if sort of P sub E is the probability that W hat is not equal to W, then we can, sorry, forgot an important term. We can write this inequality that the binary entropy of P sub E times P times the log of the support size for the first random variable, which is W, and the support size is M, is greater than equal to the sort of entropy left in the message given the estimate. Okay, any questions about this? And again, yeah, this is sort of what we used in hypothesis testing, and this is going back to the view that each code word is, or sort of each message is basically a hypothesis, and we are trying to sort of distinguish different hypotheses. So, calculating terms quickly, the P sub E is what we want to bound. This is log the number of messages, because the subword of W is just a set of messages. And we also know, kind of by definition of the rate, that this is equal to n times R. Right? R is just defined to be log M over n. So whatever is the rate. So in particular, we are claiming that when we are writing down this chain, we are saying that suppose R is achievable, and we will prove an upper bound on any achievable rate, which will then imply an upper bound on the supremum of all achievable rates. And when we say R is achievable, we mean that the probability, so we have actually a sequence of codes, and the probability of error will go to 0 as n goes to infinity. So even when the rate is fixed, we are talking of a fixed achievable rate. We are still going to allow n to go to infinity, and we are going to consider a sequence of codes with different n's. So let's just, for now, fix one of these achievable rates, fix an n, and then we will try to take a limit over n and then over R and so on. Okay. Now, let's try to compute the second term. So the entropy of W given W hat. So this, I mean, as usual, we can write it as H of W minus the mutual information of and the first term is again NR, because we have the uniform distribution over all W. That's an assumption we made. So it's log M or NR minus the mutual information. And now I claim that this is greater than equal to NR minus the mutual information between why is that?
Data processes.
Data processing. So W hat is a deterministic function of Y bar. And I can also write it as n times R minus the mutual information of X bar and Y bar, because W and Y bar kind of have a bijection between them. So for every message, we have a unique encoding. That's the assumption on an encoder. And so we kind of come down to understanding the mutual information between, so the string that is sent over the channel and what is received. And so let's try to understand this quantity. Any suggestions on how to analyze it? So recall that unlike kind of KL divergence and entropy, mutual information does not have a chain rule, as we talked about, because there are sort of two quantities, like it does, but you have to be a bit careful under certain conditions and so on. But we can write things as entropies. So we can always write this as, I guess, the entropy of X bar minus the let's write it as the entropy of Y bar. And Y bar is nothing but a shorthand for Y1 to Yn. And now let me use this notation, which is now let me apply chain rule to each of these quantities. And this is where we'll kind of use the channel properties, that because the channel is memoryless and each bit is transmitted basically independently, we know that this is equal to the entropy of Yi given Xi. What the channel does to the ith transmission only depends on the ith input. It doesn't depend on other inputs. It doesn't depend on the previous outputs. And here we can use subadditivity. So this is less than equal to the fact that conditioning reduces entropy. So this is less than equal to h of Yi. And so we get that this is less than equal to summation over I, h of Yi minus h of Yi given Xi. Which is n times the mutual information of X and Y, where, or rather, let's write it this way. For each copy Xi, Yi, the sort of the maximum value of this mutual information can be at most the channel capacity, because the channel capacity was defined to be the maximum over all distributions we could have. I mean, remember, the distribution of Y given X is just fixed. That's the channel. So the only freedom we have is choosing the distribution of X, and that determines the distribution of Y after that. And the maximum we can hope for is the capacity. So it will be at most n times the channel capacity. And so if we kind of combine everything we got so far, we had binary entropy of the error plus PE times, or rather, let's replace the binary entropy of the error by 1. So using Fanau's inequality, we get 1 plus PE times NR. So this is just based on what we had on the previous page, where I'm kind of writing 1 for the binary entropy, set of messages of size 2 to the NR. And this is greater than equal to nr minus n times c. Or if we just kind of rearrange things a little bit, we get that r times 1 minus p sub e is less than equal to c plus 1 over n, I guess. And remember, kind of r is fixed and we have a sequence of codes where n is increasing. So let's take the limit as n goes to infinity. The probability of error goes to 0. So we will get that r is less than equal to c. If we take the limit n going to infinity. And then because this is true for all achievable r's, it's also true for the supremum over all achievable r's. So in particular, the supremum r star will satisfy that it's upper bounded by the capacity of the channel. So that's kind of one side of the channel coding theorem, that the maximum achievable rate is governed by the channel capacity. We also need to show that it is actually achievable. Any questions about this before we proceed? Okay, so I'll cheat a little bit, and instead of showing this proof for the general channels, I'll only show this proof for the binary symmetric channel, because I mean, the proof for general channels is basically a slightly more careful counting, but we've already done enough counting in statistics related applications. So I'll keep this simpler, but then this will illustrate the couple of points I want from this proof. Let's just talk about the binary symmetric channel, where remember each bit is just flipped with probability p. And so let's pick, so the rate again is kind of defined as before. And the way we will construct this code is actually just randomly. So we will just kind of so x1 bar is actually a sequence of n bits. And we are going to sample each bit uniformly randomly to be 0 or 1 with probability half each. The generalization is that kind of for general channels, so there is some distribution P of X which maximizes the mutual information and the capacity of the channel. And this, as was asked earlier, is sort of is related to how we construct the encoding. So in general, we will actually sample a random code where every position of this string x1 bar is just sampled according to P of X. Here, we are using that P of X is equal to half or the uniform distribution when we are looking at the binary symmetric channel. We just proved this fact that Q equals half was the optimizer. So each bit position is sampled uniformly at random. And this is the collection of all encodings. So this is sometimes called the code book, or sometimes even simply the code, although here we are taking the code to kind of mean all of this encoding, decoding, everything. The encoding is simple. We just kind of have a bunch of m strings. We want m messages that we want to send. We will just map the ith message to the ith string that we sent, that we want to send. And we will try to send it over the channel. And so what will happen in the channel is kind of sort of maybe written in this picture and also sort of in terms of this equation. So roughly when you send a sequence of n bits. We know that every bit is kind of flipped with probability p and sent without any noise with probability 1 minus p in the binary symmetric channel. Okay. And we can sort of think about it in two ways. Either we think of some sort of geometric space where we have all bit strings of length n, and we kind of start with a string which is this xi bar, which we were trying to send. So xi bar itself, remember, is a sequence of n bits. And then we kind of take some sort of small ball around it of roughly radius sort of p times n. But it's kind of this fuzzy ball because it's not that we are changing exactly p times n positions. This is the expected number of positions we are changing, and it's concentrated around this, but we'll change roughly p times n positions. The alternate way, which is also useful, is just kind of thinking about an error vector. So another way to think is that we obtained y by adding a sequence of n bits to x, where addition was modulo 2. So addition modulo 2 just changes 0 to 1, 1 to 0. And the string we added had this kind of a p-biased coin, or just was coming, every bit was 1 with probability p, 0 with probability 1 minus p. So we started with xi bar and just moved to xi plus z, xi bar plus z. Okay. Are these two ways of thinking about it okay before we proceed? Okay. And now we need to define a decoding algorithm. So, and that's sort of the part that becomes slightly more complicated in general channels, but not too much more. Here I can sort of say it more simply as, so decoding now is not for I, but for a received sequence y bar, which I don't know which xi bar it's coming from. I just kind of received the sequence and I would like to find, so the best case scenario is that sort of y bar is somewhere here, maybe close to some xi bar, and far from others, in which case I can just output xi bar as my as my guess for what was transmitted. And I will actually say that, so if otherwise I just make no guarantees. So I will just output some garbage. Okay. So the decoding is equal to, so if I give xi bar, if, so let me denote this distance. Let me denote this distance as delta, as the distance between xi bar and y bar, which is kind of a number of positions or in which they are unequal, or the Hamming distance. Hamming distance is just the number of places in which they differ. And I'll output xi bar if I have this as the unique code word, with the distance between kind of what I received and the code word being less than equal to roughly what is the expected number of flips, which is n times, instead of p, I will kind of allow a little bit of slack, which is this my fuzzy ball, which is that, I mean, on expectation, there are about n times p bits flip, but maybe there is a little more, so I will allow for a little room for error. And I will output either sort of a garbage or sort of random code word otherwise. So basically, if this case happens, we will just count it as error. Even if we by some accident or fluke happen to guess the right thing, we will just not give ourselves any credit for it. Okay. And now it just comes down to analyzing what is the chance of error, and we will just analyze it over the choice of a random code word, so, or a random code book. So we chose this C, which was this collection of M code words, all of them chosen at random. So let's just look at the expectation over C. And if we can show that the expectation over C, the probability of error is small, then there exists a code word for which this probability of error is small. So we will just kind of calculate the expectation. What we want to compute is this quantity, which is the probability that our estimate is not equal to W. So decoding is equal to W hat or whatever. And we can break this into M possibilities that we started with the ith code word, and sort of there was a mistake. We started with the first one, there was a mistake, and so on. And now we kind of use the symmetry in the construction of the code. So if you had a code book in which kind of all zeros was the first string and all ones was the second string and something else was in other places, with equal probability, you can also have a code book in which all ones was the first string, all zeros was the second string, and so on. So there is a symmetry in the choice of the code words. Sort of for any choice, you can just kind of flip the positions of code words and you get equal probability, or sort of there is a code book with the same probability. So we can just analyze the event that the first code word was sent and there was a mistake. All of the others will have same probabilities, at least in expectation over random C. And once we come down to this, there are kind of two types of errors. One, we tried to send the first code word, but the channel kind of changed too many positions. So the Y bar was actually too far from X1 bar, and we couldn't quite recognize X1 bar because it just sort of the distance was too large. The second is, I mean, something else was close. So in this case, it was certainly not a unique code word closest to Y bar. Something else also came close to Y bar, and then in that case, we were just outputting garbage, so we'll just count that as error. So these are the two kinds of error we'll talk about. Okay. Maybe I'll leave this here and ask you to think about the bounds for both of them, since we are kind of close to ending. But I'll try to think about the bounds for both these expressions. I claim that you can use Sanoff's theorem to understand both of them, and if not, we'll discuss it next time. Any questions about what we covered so far?